Okay, now let's look at another definition. Given a positive integer m, let's be given integers a and m with m bigger than 0. We define a modulo m denoted by, so this one we usually say the class of a, equivalency class of a modulo m. So we will see about the definition of equivalency classes later. But for now, just accept this notation as the remainder R, and as you know, with R bigger than equal to 0, less than M, as a remainder R, when A is divided by M. Okay, so for example, let's say you want to find 21 mod or modulo 5, i.e. class of 21 mod 5. So this is simply, it's just a notation or just a name. You just need to find the remainder when you divide 21 by 5. What is the remainder? So we know that 21 is 5 times 4 plus 1. Right, so this is the remainder. R is equal to 1, so 21 mod 5 is equal to 1. Okay, so just we just want to say that the remainder above in division algorithm is also called A mod M when you divide A by M and you get the remainder R, or also denoted by this notation. Okay, now the next subsection, basically modular arithmetic. Again, definition, we say, so let's say given a positive integer m, we say that A charge the pencil. We say that A, given a positive integer m, we say that A is congruent B modulo m, denoted by A is congruent B modulo m if m divides A minus B. Okay, so this is a definition of congruence. When do we say that two numbers are congruent modulo another number? A is called congruent B modulo M, so the notation is this notation, similar to equivalency notation. If M divides A minus B. So two numbers are congruent if the difference is divisible by M. Two numbers are congruent modulo a number M if their difference is divisible by M. So let's look at an example. For example, can I say that 12 is, before giving the example, so if A and B are not congruent modulo M, we write A is not congruent B modulo M. Now example, let's say 12 and 5 modulo 3. Do you think 12 and 5 are congruent modulo 3? How can I know? According to the definition, I have to look at the definition. According to the definition, I have to look at their difference and see whether their difference is divisible by 3 or no. So what is the difference here? So 12 minus 5. 12 minus 5 is 7, and 3 does not divide 12 minus 5, which means 12 and 5 are not congruent. Another example, let's say 21 and 16 modulo 5. Are they congruent? Again, I have to look at the difference between 21 and 16. 21 minus 16 is 5, and 5 is divisible by 5. But that's true, therefore 21 is congruent to 16 modulo 5. Okay, now let's look at some properties of congruence. So the first property, A is congruent B modulo M if and only if, let's say B is equal to A plus Km for some integer K. So two numbers are congruent is if one of them can be written as the other one plus a multiple of M. So you could see in this example, 21 and 16 were congruent. Why? Because one of them, which is 21, was written as the other one, which is 16 plus 5. And 5 is, of course, a multiple of 5. So one of them should be written as the other one plus a multiple of M. In that case, it was 5. So how can we prove this? So this is very easy to prove. A congruent B modulo M if and only if M divides A minus B, right? According to the definition. So this part is using definition. And then when, again, by definition, so this part is the definition of congruence, then I can apply definition of divisibility. So when can I say that M divides A minus B? If A minus B is equal to, let's say, Km for some integer K. And then this is same as saying that A is equal to B plus Km. Well, it doesn't matter. I can say A is B plus Km or B is A plus Km. If I want to get B equals A plus Km, I can just take Km to the other side. So this is same as saying that B equals A minus Km. which is what I need, right? Because I need to write B as A plus some integer times M. Well, B, we wrote it as A plus some integer times M. In that case, the integer is minus K. Doesn't matter. Well, that's it. So we should just show that A congruent B is equivalent with saying that B is A plus Km, or A is B plus Km, doesn't matter. Okay, next property. Second, if A is congruent B modulo M and B is congruent C modulo M, then A is congruent C modulo M. So transitive property, you know, A is relation with B, B relation with C, then A is in relation with C. So how can I prove this? So let's see proof. So A, so let's write down the assumptions. A is congruent B modulo M. So that means M divides A minus B. So the other one says B congruent C modulo M. That means M divides B minus C. Now we know from a property from before, we know that, you know, if M divides A and M divides C, then M divides, let's say, Ka plus Lc. You remember this property we saw today? The beginning of the lecture, when we talked about divisibility, we said if M divides two numbers, then M divides any multiple of first plus any multiple of second. So in this case, I just need a simple version of it. M divides A minus B, M divides B minus C. Therefore, M divides the addition of them as well. So M divides A minus B plus B minus C, i.e. M divides A minus C. A minus B plus B minus C is A minus C. And that means A is congruent C modulo M, which is what I needed. If M divides A minus C, that means A is congruent C modulo M. Okay. Now other properties. So this was property 2. Property 3. If let's say A modulo B and C modulo D, and see if A is congruent B modulo M and C congruent D modulo M, then A plus C congruent B plus D modulo M. Proof. Let me leave this one as exercise. I'm going to give the proof for the next one, which is similar. If A is congruent B modulo M and C congruent D modulo M, then AC congruent BD modulo M. So how can I prove this one? Proof. So the assumptions here are A is congruent B mod M, which means M divides A minus B according to the definition of congruence, and also C is congruent D, which means M divides C minus D. So these are my assumptions. Now, what do I want to show? I want to show that AC is congruent BD mod M. So how can I get my goal? Well, AC congruent BD means we have to show that M divides AC minus BD. And what do I know? I know M divides A minus B, M divides C minus D. How can I make AC and BD appear? This is a little bit tricky. See, if for the first expression, if I multiply it with C, AC will appear. Similarly, second expression, if I multiply with B, BD will appear. And I know that if M divides two numbers, then it will divide any multiple of the first one plus any multiple of the second one. So why don't I? So here I mentioned the property. If M divides two numbers A and B, then M will divide any multiple of first one plus any multiple of the second one. So why don't I multiply the first number above by C, second number above by B? Why? Because so that, AC and BD will appear, and then I will add them. Okay, so if I do that, multiply the first number here by C, second number by B, and then add them, I'm going to get M divides AC minus BC plus BC minus BD. And the good news is BC will cancel with BC, and I'll get M divides AC minus BD. And this means AC and BD are congruent mod M, right? If M divides AC minus BD, that means AC and BD are congruent. Okay, so if we have two congruences, then we can multiply left-hand sides together, right-hand sides together. So this is what this property says, and we also proved it. Now, the next property is very interesting. It says if you have a congruence, A congruent B mod M, then you can raise both sides to power n for any positive integer n. So this property says we are allowed to raise both sides of a congruence to any power that we want. Okay, so let's see how we can prove this. So again, I wrote down the assumption here. The assumption, we have only one assumption here, and that is A is congruent B mod M, which means M divides A minus B. And what is my goal? My goal is to show A to power n is congruent B to power n, which means we want to show that M divides A to power n minus B to power n. So again, my job is to go from assumption to the goal. How can I do that? Well, I know that M divides A minus B. I want to show M divides A to power n minus B to power n. Now, one important property of division that we want to use here is that if M divides a number, then M divides any multiple of that number as well, right? So M divides A minus B, which it means that M will divide any multiple of A minus B. Now, can you imagine a multiple of A minus B, which can give you A to power n minus B to power n? Any multiple of A minus B that can give you A to power n minus B to power n? Well, if you know about the identity for A to power n minus B to power n, you can also know about the factor that we need to multiply with A minus B to get A to power n minus B to power n. What is the identity for A to power n minus B to power n? A to power n minus B to power n. The identity is A minus B times A to power n minus 1 plus A to power n minus 2 times B plus dot, 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 all the way to B to power n minus 1. So now M divides A minus B. So if I use the property that if M divides A, then M divides AC for any number C. If I use this property, my A here is A minus B. m divides a minus b. Therefore, m divides a minus b times this extra factor. This is my assumption. So m divides a minus b times this extra factor. But then a minus b times this extra factor will be simply a to power n minus b to power n. So this means a to power n is congruent b to power n mod m. So this is the proof. Now, you will see that there are interesting examples for this property. So one example is that find 7 to power 8 mod 3. A mod m, we said that it's a notation, according to your book, it's a notation that your book uses to denote the remainder of 7 to power 8 when divided by 3. So a mod m means if you divide a by m, you get a remainder. And the remainder, remember, is always bigger than or equal to 0 and less than m. You get a remainder with this property. That remainder is called a mod m. So 7 to power 8 mod 3 means the remainder of 7 to power 8 when you divide it by 3. How much do you think that remainder will be? But first of all, when you divide a number by 3, please note that the remainder has only 3 possibilities. It will be either 0 or 1 or 2. There is no other possibility, right? Remember that remainder is always less than divisor, bigger than or equal to 0 and less than divisor. So if your divisor is 3, then remainder will be either 0 or 1 or 2. Now, which one do you think will be the case, 0 or 1 or 2? But we start with 7 itself. We can start with 7 itself. If I divide 7 by 3, I get 1 as the remainder, right? Well, that's obvious. And this means that 7 is congruent with 1 mod 3. So here I mentioned a general statement or general fact that if you divide a by, let's say, number b and you get a remainder r, then a and r, the number and the remainder are always congruent to each other, mod divisor. Why is that true? Well, I just mentioned here. So let's assume you have a number a and you divide it by b, you get the remainder r. So what does that mean? That means a is equal to bq plus r. So if I take this r to the other side, I'm going to get a minus r equals bq. And a minus r equals bq means b divides a minus r, right? Because if a minus r is a multiple of b, that means b divides a minus r. And b divides a minus r means a and r are congruent mod b. That's the definition of congruence. So I showed that here in general, whenever you have a number a, you divide it by b, you get remainder r. The number and the remainder are congruent. And in particular, in this case, when you divide 7 by 3 and you get 1 as the remainder, 7 and 1 are congruent. Of course, in this case, it's easy to directly justify this, verify this. 7 minus 1 is 6, which is divisible by 3. Of course, you can easily do that and verify it that way. But here, what I wrote here shows that in general, this is always true, that any number is congruent with its remainder. In this case, 7 congruent with 1. Okay, now what do we need? We need 7 to power 8. Look at the question again. The question talks about 7 to power 8, the remainder of 7 to power 8 when divided by 3. And I have 7 right now. How can I get 7 to power 8? Starting from 7, I can just raise both sides to power 8. If I raise both sides to power 8, by property 5 above, so I said property 5 above, property 5 is about this property that we can raise both sides to any power. So here, I have 7 to power 8 congruent to 1 to power 8 mod 3 when I raise both sides to power 8. And 1 to power 8, as you know, is 1. So that means 7 to power 8 congruent 1. And but we just said that any number is congruent to its remainder, right? So the remainder has to be 1. 7 to power 8 congruent to 1. So that means the remainder has to be 1. Okay. Now let's look at another example. Let's say, for example, if you want 8 to power 8, let's say, instead of 7 to power 8, if you want to find the remainder of 8 to power 8 when divided by 3, how much do you think the answer would be in that case? Let me charge the pencil. So next example, find 8 to power 8 mod 3. So if I start with 8, so again, we need 8 to power 8, but again, similar to previous example, let's start with 8 itself. 8 is congruent to which number mod 3? Congruent to its remainder, we just said, right? Each number is congruent to its remainder. Mod divisor. Divisor is 3 here, and the remainder of 8 divided by 3 will be 2. So if I raise to power 8, I'll get 8 to power 8, congruent 2 to power 8, mod 3. Okay, this time is a little bit more complicated than previous case, because previous case in the right side, we had 1 to power 8 and 1 to any power is 1. But here we have 2 to power 8. So what can I do with this? 2 to power 8. Well, of course, one way is to calculate 2 to power 8 and find its remainder when divided by 3. But let's try to do as little as computation as possible. So 2 to power 8, well, let's think about it. For example, 2 to power 4, we know it's 16, right? Which is congruent 1 mod 3. And 2 to power 8 is 2 to power 4 raised to power 2, right? So I am doing a small trick here. So in order to reach 2 to power 8, I want to start with 2 to power 4, which I know it's 16 and has remainder 1. And then raise it to power 2 to get 2 to power 8. So now 2 to power 4 equals 16, congruent 1 mod 3, right? 16 is the remainder of 16 when divided by 3, of course, is 1. So then that means 2 to power 8 is 2 to power 4 to power 2, congruent 1 to power 2 mod 3. 2 to power 4 is congruent 1. So 2 to power 4 to power 2 is congruent 1 to power 2. 1 to power 2 is 1. That means 2 to power 8, congruent 1 mod 3. But 2 to power 8 itself was congruent 8 to power 8. So that means 8 to power 8, congruent 1 mod 3. That means 8 to the power 8 mod 1 mod 3 equals 1. So again, 8 to the power 8 mod 3 means remainder of 8 to the power 8 when divided by 3. And we just showed that this is 1. So this is one solution. Let me do it with another solution, solution 2. Okay, so what was the issue here? We had a small issue, and that's when we got 2 to the power 8, and 2 to the power 8 is not as simple as 1 to the power 8. Well, sometimes this situation is inevitable, and we cannot get 1. We get a number other than 1, and we have to raise it to some power, and of course, we have to do some calculation. But sometimes we can avoid this situation, and also in this case. How? Well, because in addition to 1, finding powers of -1 is also extremely easy. 1 to any power is 1, well, that's extremely easy, but -1 to odd powers is -1, -1 to even powers is 1, so that's also extremely easy. So sometimes we can relate things to -1 to avoid computations. Well, 8, now in this case, remember our base is 8, and we are talking about 8 mod 3. So yes, 8 is congruent to 2, that's true, but also I can also say that 8 is congruent to -1. Remember, this congruence is not unique, you know, a number can be congruent to infinitely many numbers. So 2 is one of them, and they don't have to be positive either. The number which has to be positive is the divisor, but these numbers here could be positive or negative. They're allowed to be positive or negative. So solution 2, I want to start with, so note that 8 is congruent to -1 mod 3. Why? Because how can I say that, or when can I say that two numbers are congruent? If their difference is divisible by number m. So here 3 divides 8 minus -1, right? The difference between 8 and -1 means 8 minus -1, which is 9, and 9 is divisible by 3. So I can say that 8 is congruent -1 mod 3. Well, you could tell me that -1 is not considered as a remainder, because the remainder has to be always non-negative. Remember, we said r bigger than or equal to 0, less than m. Well, that's true, but I did not say that -1 is remainder. I'm just saying that 8 is congruent -1. But the remainder of 8 divided by 3, of course, is 2, not -1. But I did not claim that -1 is the remainder. I'm just saying that 8 is congruent -1. So instead of 2, I use -1. Why? I just told you the reason, because in the next step, I want to raise both sides to some power, right? And finding -1 to any power is extremely easy to compute. So if I raise to power 8, 8 to power 8 congruent -1 to power 8, and -1 to power 8 is 1, -1 to even power is 1, so that means 8 to power 8 congruent to 1 mod 3, well, which means that 8 to power 8 mod 3 equals 1. So the remainder is 1. So we got the same answer as the solution 1, but we got it faster because we could make -1 appear, and -1 to any power is very easy to compute. So with a similar method, even for example, let's say find, even if the power is very big, for example, let's say 8 to power, let's say 2010. mod 3. Again, you can do a similar computation. 8 is congruent minus 1 mod 3 raised to power 2010. And again, minus 1 to power 2010 is 1. So that means 8 to power 2010 congruent 1 mod 3, which means 8 to power 2010 mod 3 equals 1. Let me give you another example. Let's say, for example, find let's say 42 to power 14 mod 13. Or mod, let's say 15. So again, this notation means what means we want to find the remainder of 42 to power 14 when it's divided by 13. Okay, so previous cases we had 1 or minus 1, but here, see, I cannot say 42 is not congruent 1 because 42 minus 1 is 41, not divisible by 15. Even if I say minus 1, 42 is still not congruent minus 1. Okay, so it seems that the screen is freezed. So let me stop share and share again. Yeah. So 42 congruent 1 is not true. The difference between 42 and 1 is not divisible by 15. Difference between 42 and minus 1 is not divisible by 15 either. So what options do I have? If you divide 42 by 15, I can say 15 times 2 plus 12, right? So I can say 42. Remember, each number is always congruent with its remainder. So I can say 42 congruent 12 mod 15. And then I have to raise to power 14. But 12 is too big. If we can replace it with something, I mean, ideally 1 or minus 1, but if not possible, at least something smaller than 12 in absolute value. By smaller, I mean smaller in absolute value, because the sign, I can take care of the sign. If it's negative, I know that negative to odd powers remains negative, to even powers becomes positive. I just care about absolute value. So 12 is too big, relatively big. Can I replace it with something smaller? Well, 12 itself is congruent with minus 3, right? 12 and minus 3 are congruent, mod 15. Why? Because the difference between 12 and minus 3 is 15 itself, which is, of course, divisible by 15. So instead of 12, I can replace it with minus 3, and it's easier to find powers of minus 3 because 3 is a smaller number compared to 12. So 42 to power 14, now I can raise to power 14, 42 to power 14, mod 15, and it's congruent with minus 3 to power 14. And minus 3 to power 14, of course, is same as 3 to power 14. Now I need 3 to power 14 mod 15. How can I do that? Again, I want to avoid computations as much as possible. So 3 to power 2 is 9. 3 to power 3 is 27. So let's start with 3 to power 13 and 3 to power 3, which is 27. And 27 is congruent minus 3 mod 15. My goal is to try, to make, the small numbers basically appear rather than big numbers. So 3 to power 3 is 27 is big, but can be replaced with minus 3 mod 15. Why again? Because 27 and minus 3, their difference is 30, which is divisible by 15. So 27 and minus 3 are congruent, and this is 3 to power 3. What do I need? So I'm I have 3 to power 3 here, which is congruent minus 3. I need 3 to power 14. How can I get 14 from 3? I have to raise both sides to power. Well, if I raise to power 5, I get 15, but I need 14. So 5 is too big. Why don't I raise both sides to power 4? And then I'll get 12. Well, you may tell me, okay, I need 14. Why 12? But once I have 12, 3 to power 12, I can just multiply by 3 to power 2 to get 3 to power 14. So let me raise to power 4 both sides. Raise both sides to power 4. Then we get 3 to power 3 to power 4 plus 3 to power 12, which is same as minus 3 to power 4. I'm raising to power 4 mod 15. Okay, and this is again 3 to power 4. So then I need, so this is 3 to power 12. As you can see here, this is 3 to power 12. Can multiply both sides with 3 to power 2. Then I get 3 to power 14, congruent with 3 to power 6. So see, from 42 to power 14, we reduced the numbers and powers, everything. I got 3 to power 6 now. 3 to power 6, still we can reduce it. How can I reduce? So lastly, remember 3 to power 3 was 27, which was minus 3. We already used this fact once. I want to use it one more time. Mod 15. I need 3 to power 6. I need 3 to power, I know that 3 to power 3 is minus 3. How do I get 3 to power 6 from 3 to power 3? Just raise to power 2. Raise to power 2. Get 3 to power 6. Congruent with minus 3 to power 2, which is 9. Well, that's it. 9. So the 3 to power 3 was minus 3. I raised both sides to power 2. Minus 3 to power 2 is 9. And 9 is my remainder. So that means 3 to power 6, congruent 9. And that means this is the same as my original number, right? Mod 15, 42 to power 14. And this means 42 to power 14 mod 15 equals 9. So we're able to calculate the remainder of 42 to power 14 when divided by 15. Without calculator, of course, 42 to power 14, it's a big number. But without calculator, we could find the remainder when divided by 15, just using the properties of congruence, that we can raise both sides to some power, for example, right? And of course, you can use your calculator, for example, or a software to verify that this is actually the remainder. All right. Okay, so let's start section 4. So 4.3. Section 4.3 is about prime numbers and greatest common divisors. 4.3 prime numbers and greatest common divisors. So let's start with definition of a prime number. So let's say p bigger than 1 be an integer. We say that p is a prime number if its only positive divisors or factors are 1 and p. Okay, so if a number has only two factors, 1 and the number itself, then that number is called a prime number. And of course, by definition and by convention, a prime number has to be positive. So for example, p equals 2. Is p equal to a prime number? Is a prime number. Why? Again, because the only divisors or the only factors of 2 are 1 and 2. So 2 is only divisible by 1 and only divisible by 2 and nothing else. What about, let's say, p equals 3? P equals 3, again, a prime number. The only factors are 1 and 3. P equals 4, not a prime number. Why? Because 2 is a factor of 4, right? So if a number has a factor other than 1 and the number itself, then the number is not prime. So 4 for p equals 4, 2 is a factor and 2 is not 1 and not the number itself. So that means 4 is not a prime number. P equals 5 is a prime number. And so on. So how can we check that whether a number is prime or not? So for example, let's say p equals 93. Do you think it's prime or no? Well, if you want to see whether, for example, 93 is a prime number or no, well, we have to see whether it's divisible by any number other than 1 and itself or no. So that means we can start with 2, right? So 93 divided by 2, see whether it's divisible or no. In other words, 2 does not divide 93, right? And then we go to the next number. And so on. So 92 does not divide 93, right? So if it does not have any other divisor, then it must be prime. But well, this is going to be too long, right? So we will see that we don't have to check all the numbers less than the given number to check whether they are divisors or no. it's enough to check only up to square root of the number. So let me mention as a remark here. So remark to check whether a given number is prime or no, it is enough to check whether there exists a prime number. It's a given number n is prime or no. It's enough to check whether there exists a prime number p, which is less than or equal to root n, and it divides n. If the answer is yes, then n is not prime. The answer is no, n is prime. So we don't have to go all the way until n. We don't have to check all the numbers until n. Just prime numbers and prime numbers until root n is enough. So let me give you an example. Like I said, for example, p equals 93. Or let me say n equals 93. How much is square root of 93? Square root of 93 is 9 point something, right? So if n is not prime, then it must have a prime factor less than or equal to 9 point something. So if n is not prime, then p equals 2 or 3 or 5 or 7 must be a factor for n. See, this is what the remark says. Check whether there is a prime number p which is less than or equal to root n and it divides n. If the answer is yes, n is not prime. If the answer is no, n is prime. So I have a number n. First calculate root n is 9 point something. Then check the prime numbers which are less than or equal to this number. Which prime numbers are less than or equal to 9 point something? Well, 2 is one of them, 3 is one of them, 4 is not a prime, so I didn't list it. 5 is one of them, 6 is not a prime, I didn't list it. 7 is one of them, 8 is not a prime, I didn't list it. 9 itself is less than 9 point something, but again, 9 is not a prime, so I didn't list it. So if it's not a prime, this number n, if it's not prime, either 2 or 3 or 5 or 7, one of these numbers, at least one of these numbers must divide n. But do they? Well, this is now very easy to check. So instead of checking 92 numbers, whether they are a factor for 93 or no, I just need to check 4 numbers, 2, 3, 5, and 7. So if none of these 4 numbers is a factor of n, then that's it. And that means n is prime. So easy to check that 2 does not divide 93 because 93 is not even. 3 does not divide 93. So 3 divides 93. 3 divides 93 because 93 is 3 times 31. 5 does not divide 93 and 7 does not divide 93. So that means, see, one of these numbers, one of these 4 candidates divides 93. So we said that if the answer is yes, if one of the numbers divides, then n is not prime, because of course it has a factor other than one in itself, at least one factor, which is 3, and 3 is not 1 or 93 itself. That means 93 is not prime. But let me, for example, if I want to give another example, let's say, for example, 97. What about 97? Again, root 97 still is 9 point something. So again, need to check. P equals 2, 3, 5, and 7. Whether they are factors of n. Well, 2 does not divide 97. It's not even. 3 does not divide 97. How do I know? I think you know from middle school that if the sum of digits is not divisible by 3, then the number is not divisible by 3. 9 plus 7 is 16, not divisible by 3, so number is not divisible by 3. 5 does not divide 97 because multiples of 5 end in 0 or 5. The last digit should be 0 or 5. But for 97, last digit is 7. And 7 does not divide 97 again. Because 97, if you divide it by 7, you're going to get 13. So 97 is basically 13 times 7 plus 6. So the remainder is 6, not 0. So 7 does not divide 97 either. So I only need to check these 4 numbers, nothing else. So none of these 4 numbers divide 97. So that means n equals 97 is prime. Okay, now I want to prove this remark. So proof of remark. First, we state an important theorem called fundamental theorem of arithmetic. So I haven't started proof yet, so I can say we will provide a proof for remark above shortly. So first we state fundamental theorem of arithmetic. What does it say? It says that every integer greater than 1 is either a prime number or it can be written as product of 2 or more prime numbers. Every number is either a prime number itself, or it can be written as product of two or more prime numbers. So this is called fundamental theorem of arithmetic. So for example, let's say if I say 22, I can write it as 2 times 11, product of two prime numbers. Or let's say, for example, 50. 50, I can write it as 5 times 5 times 2. Product of 3 prime numbers. 2 of them are the same, but that's okay. Which can be also written as 5 to the power 2 times 2. So any number can be written as product of 2 or more prime numbers. This is called fundamental theorem of arithmetic. Now let's, using this, we can prove the remark. So proof of remark above. So what do we want to show? We want to show that if n is not prime, then there exists a prime number P, which is a factor of n, and P is less than or equal to root n. So this is what we want to show. It seems that the screen is freeze, so let me stop share. Okay. So we want to show that if n is not prime, then there exists a prime number P, which is a factor of n, and P is less than or equal to root n. That's what the remark says, right? In other words, if there is no prime less than root n, which is a factor of n, then the number has to be prime, right? For example, here we saw that 97, among the primes that are less than root n, none of them are factor of n, and then we concluded n is prime. So we can state it that way, that if n is not prime, then at least one prime number P less than root n must be a factor of n. In other words, if there is no prime number P less than root n, which is a factor of n, then that number must be prime. So you know the equivalency, right? Between P implies Q and the contrapositive negation Q implies negation P. You know that these two are equivalent. So right now I want to prove this version, that if n is not prime, then there is a prime number P, which is factor of n, and P is less than or equal to root n. So first, note that n is equal to AB with, if we say n, note that n can be written as n equals AB with A between 1 to n and B between 1 to n. Right? My assumption is that since n is not prime, my assumption is that n is not prime. If n is not prime, it can be written as product of two numbers, and none of those two numbers are 1. Therefore, both of them are between 1 to n. So if n is not prime, it has a divisor other than 1 and itself, right? So let's say it has a divisor, for example, a, which is not 1 and not itself. So if A is bigger than 1 and less than n, B has to be also bigger than 1 less than n, right? Because when can B would be n if A is 1, but A is bigger than 1, so B is less than n. Similarly, B would be 1 if A is n, but again, A is less than n, so B is bigger than 1. So any number which is not prime can be written as product of two numbers, both between 1 to n. Only prime numbers can be written as 1 times the prime number only, but other numbers can be written as product of two numbers, both between 1 to n. Okay, so now A is less than or equal to root n, or B less than or equal to root n. See, I have two numbers A, B with this property that I said, both between 1 to n. Now I'm saying one of these two numbers has to be less than or equal to root n. Why? Because otherwise, what can I say? I can say that A will be bigger than root n and B bigger than root n. Please remember, P or Q, negation of P or Q is negation P and negation Q, which would imply AB bigger than N, i.e. N bigger than N. AB, remember it was N, and N bigger than N is impossible, or contradiction in other words. So therefore we can say that A is less than root N, or B is less than root N. Now this A itself, so if A is less than root N, again, I can have two possibilities. If A itself is prime, then N has a factor, has a prime factor, which is less than or equal root N. Remember what was my goal? My goal was to show that N was not prime. That was my assumption. Okay, again. Yeah, I think it was freeze, but now it's okay, I think. Again, what do I want to show? I want to show if N is not prime, then N has a prime factor, which is less than or equal to root N. Now, if A is less than root N, again, there are two possibilities. If A itself is a prime, then N has, because remember, A was a factor of N is equal to AB. So A is a factor of N. So if A is prime, so that means N has a prime factor, which is A, and is less than or equal to root N, because my assumption here is that A is less than or equal to root N. And if A is not prime, then A has a prime factor, let's say P1, which is less than or equal to A, by fundamental theorem of arithmetic. Fundamental theorem of arithmetic says if a number is not prime, then it has a prime factor. Every number can be either prime or can be written as product of primes. So if A is not prime, then it has a prime factor. I call it P1. Of course, P1 is less than or equal to A, right? Because any number, if you have a factor of another number, everything is positive. So if you have a factor of another number, the factor is always less than or equal to the original number. Now P1, so what can I say? So say A equals, let's say P1 times C. Right? Because P1 was a factor of A. So what does that mean? N was equal to AB. So then I can say N equals P1 times C times B. And what does that mean? That means P1 is a factor of N. I wanted to show that N has a prime factor which is less than equal to root N. I found the prime factor P1. Is it less than equal to root N? And P1 is less than equal to A, but A itself was less than equal to root N. So these two together gives me what I needed. I was looking for a prime factor for N, which is less than equal to root N. There you are. P1 is a prime factor for N, which is less than equal to root N. So I considered two cases here, C1 and 2. In each of these two cases, I'm done. I showed that my number N has a prime factor, which is less than equal to root N. So this is for the case that if A is less than equal to root N, but a similar argument can be given if B is less than equal to root N. So what did we show? So we showed if N is not prime, then it has a prime factor which is less than or equal to root N, which means we proved the remark. Okay, guys, so that's all about prime numbers for today. And next time we'll show that there are infinitely many prime numbers. So today we gave an algorithm basically how to check whether a number is prime or no. So there are some numbers, of course, some numbers are prime, some numbers are not prime, but the question is, are there finitely many prime numbers or infinitely many prime numbers? Next time we'll show that there are infinitely many prime numbers. Okay, so see you next week.